Hello everybody and welcome back. We're looking at question number 2, or I guess problem number 2, on the 2017 winter midterm for 1501. So we got two parts. I think most of the questions here have two parts. A part and B part. A, state the definition of a convergent series. In other words, fill in the blank. The series, so this sum here, it's infinite series, is convergent if... So we only had one definition that we learned, and that is if the limit of the partial sums I guess they use an N. I'll switch it to a K. So if the limit of that exists. Another way you could say it, so other things you could say if the sequence Sk is convergent. That would be another thing you could say. Variations on these, but this is the main idea. So, and this was how we built up just about every test we did in class. Either we used a previous test to create our new test, like root and ratio, we used the comparison test. But things like integral test, comparison test, we built them up out of partial sums. Okay? Because that is the definition. So we just built off the definition. We're just going through and dealing with the SNs and the SKs. While it will work, it's not always the easiest thing to do. But we can't forget that definition, and usually every year there's a question that is just pure, do you remember that it's about the partial sums? No other test will work, is it just a partial sum sort of thing? And that's what we've got here for B, at least I'm pretty sure that's what we've got here for B. So suppose the ANs are non-negative, and the SN, which is the sum of the A1 through ANs, is less than or equal to 100 for all N. Prove that the series is convergent. Okay, so we're going to use the monotone convergence theorem. Now, how do I know? How do I know? Well, I don't know anything about the AIs. I have no idea. Is AN 1 over N, or is it ln N over N squared minus 5? Like, there's no information. Nothing that tells me about it. So I have to sort of rely on theory when I'm in this position. I have a few sort of building blocks that I can use, but I've got to do something, and the fact that they've told me about the SNs makes me think, okay, well, these ANs, this is convergent, by definition, exactly when the limit of the SNs exists. So, how do I show that the limit of the SNs exists? And I take a look at the information they've given me about the SN, and I say, alright, they've given me the SN, they remind me what it is, just in case I forgot, as though we don't study for our tests, but they give me the SNs, and they tell me it's always less than or equal to 100. Now, on its own, this doesn't tell me what SN is. There's no way to know exactly what SN is. There's lots of functions that do this. But knowing that the SNs are always bound above by something, I seem to recall that being mentioned every once in a while in class. We're going to use the monotone convergence theorem. We've got an upper bound for the SNs. I just need to show that the SNs increase. And that's what the condition about the AN being non-negative is going to tell us. Okay. So I might say something to the effect of, notice that since AN is non-negative, Sn minus n minus 1 which is AN. Actually, let's write this out a little bit. Then Sn, there we go. Sn minus 1, which is just A1 plus A2 plus all the way up to AN minus 1 plus AN minus A1 plus A2 plus all the way up to AN minus 1. But most of these are going to cancel everything except an, and so this is going to be greater than or equal to 0. So what does this tell me? Sn is greater than or equal to Sn minus 1. So we see the Sn sequence is monotone. S1 is going to be a lower bound, and we just keep going. Well, not that we keep going up, it's just that we never go back down. So we might say it's not a series. Series are when we add things up. So our sequence is bounded. Specifically, we might say by S1 and 100. And it's monotone. Well, then that tells me, and we have to remember these results. We mentioned it in class. It's also in your textbook in case you're just the sort of person who reads out of the textbook. The limit here exists by the monotone convergence theorem. But if the limit there exists, then this sum here must be convergent. And we're done. Everything's all squared away. And that finishes up question number 2. Up next, of course, question number 3. I'll see you then.